Hello. So I guess it's time for the chain rules, and here's the first one. Although they're really all the same. It's just different situations, different number of variables, whether you have 3 independent variables or 2, and then whether each of those variables depends on 1 or 2 parameters. So this is the first one. It's the easiest one, where w is a function of x and y, and x and y are both functions of t, and these are all differentiable functions. Then w is a function of just t, right? You can sort of eliminate the x and y's and write it simply as a function of t, and it's a differentiable function of t, and, well, here's its derivative, right? So the derivative of w with respect to t is just going to be the x partial of w times the derivative of x plus the y partial of w times the derivative of y. And this is the other version of it. I find that a little confusing, so I usually remember it the first way. Of course, it's on your formula sheet, so you don't have to remember it, although once you get used to it, it's really not that hard to remember. After all, it looks like you can cancel the dx and dy's, although not really. It doesn't really work that way, but it kind of looks that way, right? So maybe we should prove this. I know we're not going to prove a lot of things, and if you don't like proofs, you can skip ahead 5 minutes or so. So let's start with the fact that w is given and it's differentiable. So since w, which is a function of x and y, is a differentiable function, that means we can write delta w as the following, right? We can write it as the partial of w with respect to x times delta x plus the partial of w with respect to y times delta y plus epsilon 1 times delta x plus epsilon 2 times delta y, where epsilon 1 and epsilon 2 both approach 0, as delta x and delta y approach 0. Okay. And so the next thing to do is just divide by the delta t. So divide both sides by delta t. That means you're dividing each term by delta t, right? Right. And then just take the limit as delta t approaches 0 on both sides. So when you take that limit on the left, you just get the derivative of w, right? And then on the right, you get partial of w with respect to x, and then this is the ordinary derivative, right? X only depends on t. So the derivative of x with respect to t plus the y partial of w times the derivative of y plus, so this is going to be epsilon 1 times the derivative of x plus epsilon 2 times the derivative of y, although we don't really need that because notice what happens as delta t goes to 0, delta x and delta y go to 0, which means epsilon 1 and epsilon 2 also approach 0. And so what you're left with is the chain rule. I don't mind writing it all over again. Right. And that's all we wanted to show. So it just comes down to the fact that when delta t goes to 0, right, g and h are differentiable, right? And so, right, so the epsilon 1 and epsilon 2 also goes to 0. Okay. So that's just a quick proof there. But let's see how we can use it in practice. Okay, so we're given w as a function of x and y. It's just x squared plus xy minus y squared, where x is just cosine of t and y is sine of t. So we want to find the derivative of w with respect to t. Okay, so we're just going to use the chain rule again. So this is partial of w with respect to x times the derivative of x plus partial of w with respect to y times the derivative of y. So we have four things we have to find. We have to find both partial derivatives of w. So let's do that down here. With respect to x, you get 2x plus y. And then with respect to y, we get x minus 2y. Right? All right, so the derivative of x, well, the derivative of cosine is negative sine, right? And then the derivative of y is the derivative of sine, which is cosine. So putting this all together, right, we get, let's see, 2x plus y times negative sine of t plus x minus 2y times cosine of t. Right. Unfortunately, there's something a little unsatisfying about this answer. One, we can multiply it all out, but also it depends on, it looks like three variables, right? X, y, and t. Ideally, because this is the derivative with respect to t, we would like this strictly as a function of t. And, in some cases we may not be able to do that, but here, 2 times x is really just 2 times cosine of t, right? Plus y, that's sine of t, times, again, a negative sine t. I should have put that negative in front here. Maybe let's do that now. So this is equal to, negative what I just said times sine t, right? Plus, and then x is cosine t minus 2 times sine t times cosine t. So now we can expand it all out. We get negative 2 times sine cosine minus sine squared of t. And then we get plus cosine squared of t minus 2 sine cosine. So I don't know how else we can put this all together. We get cosine squared of t minus 4 sine t cosine t minus sine squared of t. I think that's probably good enough. If you really want to go one step further, right, cosine squared minus sine squared is just cosine of 2t, and then sine, sine t times cosine t is 1/2 sine of 2t, so this is minus 2 times the sine of 2t. But either way is fine. Right? Yeah, just don't leave it like this because, again, you're mixing your x's and y's and t's together. Write it all as a function of just t, either way. Okay. Yeah, so that's using the chain rule. In this example, of course, we didn't need to use the chain rule, right? What we could have done is just write w as a function of t by itself. And we do that by just, substituting x and y in the original expression for w, right? So if we do that, we get what? We get, let's see, x squared is cosine squared, cosine of t squared, plus cosine times sine, plus, or minus, I should say, minus y squared is minus sine squared. So, yeah, you get cosine squared plus sine times cosine, and then minus sine squared. Right? And now that's just w as a function of t. So at this point, you don't need me. This is Calc 1 at this point, right? Just take the ordinary derivative of w with respect to t. Yeah, so it's a Calc 1 problem. And not a hard one either. Just make sure you know either the product rule or the chain rule, or in this case, both. So here you're going to get -2, I was going to put the sign first, -2 cosine t sine t. And now the product rule, right? Sine times negative sine is going to be, well, let's do it the other way. Cosine times the derivative of sine, so that's cosine squared, and then minus sine squared, and then -2 sine t cosine t. And so you get the same thing, right? You get cosine squared t -4 sine t cosine t minus sine squared t. And when you simplify, you just get the same thing, cosine of 2t minus 2 sine of 2t. And either way. Okay, so you might wonder then, I'm sure your question is then why did I need the chain rule if I could just do this directly by first substituting, get w as a function of t, and then just taking the ordinary w of t. Right? So that's a good question. And in this example, of course, you're right. We didn't need the chain rule, right? We could do it either way. But then, there could be other examples where you might not be able to do it directly. You might have to use the chain rule. So let's see one of those. So here's an example. We're given z as a function of x and y. It's just e to the xy. But we're not given x and y in terms of t, right? They're just some unknown functions, right? X is some function of t, f of t, and y is some other function of t, say g of t, right? And we're not given those functions, but we are given the values of those functions, right, at t equals 0, right? So this is just saying if t is 0, right, then we know that x is 3, y is 2, and we know the derivatives too, right? The derivative of x, again, at t equals 0 is 2, and the derivative of y at t equals 0 is 4, right? So I didn't write down the question yet. The question is to find the derivative of z at t equals 0. Okay? Yeah, so I don't think there's any way around it. In this case, we simply have to use the chain rule, right? Simply because we can't really plug in these unknown functions. I mean, you can write it formally as e to the f of t times g of t, right? And you can evaluate that. You can find z at t equals 0, but then you won't be able to take the derivative, right? So I think the way to go here is just use the chain rule. Right? All right. So the partial of z with respect to x, all right, so that's going to be y e to the xy. And then the derivative of x with respect to t, well, that's just f prime of t, right? Plus, and then the y partial of z is going to be x times e to the xy. And then the derivative of y is just g prime of t, right? So now we can plug in t equals 0. Make that a little bit neater here. So t equals 0, right? So yes, when t is 0, y is 2. So this is going to be 2 times e to the xy. So x times y is 6, right? And then f prime of 0 is 2, right? Plus x e to the xy. So x is 3, and e to the xy is e to the 6. And then g prime of 0 is 4. So I think we get 4 e to the 6 plus 12 e to the 6. So 16 e to the power 6. Okay? So, yeah, right, because we're not given x and y explicitly in terms of t, right? We have no idea what those functions are. The best we can do is just use these numerical values and substitute them in using the, using the chain rule. Like I say, there might be another way. You can do this directly by just substituting, but I find this way just much easier. So, right. And, it could be the reverse. It could be the function, z as a function of x and y might be unknown. And, x and y might be explicit explicit functions of t. So it could be the other way as well. All right. Okay, so here's another chain rule. Again, w is a function of x and y, but now x and y depend on two parameters, s and t. Right? So suppose all three of these functions are differentiable, then you have, well, there's two derivatives of w. There's the partial of w with respect to s, and the partial of w with respect to t. Right? After all, w is a function of x and y, but x is a function of s and t, and y is a function of s and t. So indirectly, f depends on s and t. Right? So by eliminating x and y, you can solve for w in terms of s and t, right? By substituting, right? Just like we did earlier. And so now the question is, right, what's the partial of w with respect to, s? Not x, but s, right? Or if you prefer, f subscript s. And partial of w with respect to t, or f subscript t, right? But we have the answers. Again, it's just provided by the chain rule. Right? So there's no need to prove this one. It works just the same as the other, the previous chain rule, right? Right. So we'll just do an example. Okay, so w is a function of x, y, and z, and x, y, and z are functions of t and s, right? So first we want to find the partial of w with respect to, let's do s first, and then we'll find the partial of w with respect to t, right? And in fact, this theorem doesn't even cover that, right? Because we need z as a function of s and t as well. But you see, you just get one more term here, right? In other words, for the t one, you'll just get plus partial of w with respect to z times the partial of z with respect to t as well, right? So you just add that one extra term. So we'll do that here, right? So so partial of w with respect to x is just 2, and then the partial of x with respect to s is 0, because e to the t is a constant with respect to s, right? Plus, and then partial of w with respect to y is just 5, and then partial of y with respect to s is 2 e to the 2s. And then partial of w with respect to z is 3. And then partial of z with respect to s, well, right, this is just e to the t times e to the s. So I think you just get the same thing, right? e to the t plus s. Yep. So you just get 10 e to the 2s plus 3 e to the, I'll write it the same way, t plus s. Right? Yeah, I thought it was going to be a little bit harder, but okay. And then partial of w with respect to t. Okay, thought I would save some space here. So with respect to t, so we still have the x partial of w, that's still 2. And then with respect to t, the derivative of x is e to the t. Plus, right, the y partial of w is 5. And then with respect to t, e to the 2s, the derivative of that is 0. It's a constant, right? Plus 3 times, and again, it's just e to the t plus s. With respect to t or with respect to s, doesn't matter. So you get 2 e to the t plus 3 e to the t plus s. And yeah, we can factor out the e to the t here. I wouldn't bother. Right, so that's all it is. Just, right, very direct using the chain rule. Right. Of course, we can go more direct by finding w in terms of, right, in terms of s and t. If you want to do it that way, fine, because it's just, right, 2 e to the t plus 5 e to the 2s plus 3 e to the t plus s. And now, just take the, partial derivatives of this with respect to s and t, and you should get the same thing. So, it's not much easier that way, in my opinion, but it does give you the same two answers. All right. So that's the other chain rule. And of course, you can add more terms if you have w as a function of x, y, z, and r. And then r is a function of, s, t, and u, right? So you just get more terms and more derivatives. But in most practical cases, this is all we'll need. Okay, so we have a related topic of implicit differentiation. So let's see how that works, right? Suppose we start with a function, let's say w, and I'll write as capital F, a function of x and y. Okay. Right, and suppose this just is some equation. This just equals 0, right? And then we have one of the, right, suppose we have y as a function, say little f, as a function of x. Okay. Then what we can do is write w strictly in terms of x, right? Because y is a function of x. And so this is just some function of x, right? And it still equals 0, right? Either way you write it. So now we can just use the chain rule to find the derivative of w, right, with respect to x. So by the chain rule, you get partial of f with respect to x, right, times the derivative of x with respect to, well, x, right, plus partial of w, partial of w, which is also the partial of f with respect to y, right, times the derivative of y with respect to x. And this equals 0, right? Well, it's, right, the derivative of 0 is still 0. So, yeah, this still equals 0, right? Right, and of course, the derivative of x with respect to x is just 1. So we have partial of f with respect to x plus partial of f with respect to y times the derivative of y. So we're looking for the derivative of y, right? So I'm going to subtract off the partial of f with respect to x from both sides. And that gives us this equation now, partial of f with respect to y times the derivative of y. And that's going to equal negative partial of f with respect to x. So now we just divide both sides by the y partial of f. So these cancel, and we end up with, well, I'll write it over here. The derivative of y is just negative, right, partial of f with respect to x divided by partial of f with respect to y. And if that looks really awkward to have a fraction within a fraction, let's use the more succinct notation of using subscripts, right? Remember, another way to write the partial of f with respect to x is just f subscript x, and likewise f subscript y for the denominator. Okay. So this allows us to find, rather directly, the derivative of y with respect to x, right? In terms of both partial derivatives of w. Okay. All right. So that's implicit differentiation. Okay, so we're looking for the derivative of y, dy by dx, for the equation x to the fifth minus 4xy squared plus 2y cubed equals 12. All right, so this is something you've done before. Way back in Calc 1, right? This is nothing new. First thing you might try is, can we solve for y here? And write y explicitly as a function of x. And, I mean, technically the answer is yes, because it's a cubic equation, and there is a formula for cubic equations. But I don't know it. I certainly don't have it memorized. I can, So basically here the answer is no. We're not going to be able to solve this for y explicitly in terms of x. Not easily, right? So back in Calc 1, of course, you were told just take the derivative of both sides. Right? So that's one way to do this. This is a good reminder of that. Oh, I'm sorry, derivative of 12, which will be 0, of course. Right? So the left side, you're just going to get 5x to the 4, and then minus, let's see, 4x times 2y times the derivative of y, so minus 8xy times the derivative of y, and then minus 4y squared, right? Don't forget the product rule, right? And then plus 6y squared times the derivative of y, and the derivative of 12 is 0, right? So let's see, right? So the rest is just algebra. Let's factor out the derivative of y here. You factor it out, you get 6y squared minus 8xy. And you add the 4y squared to both sides. You subtract the 5x to the 4 from both sides. That's a 5, not an s. Right? And then just divide both sides by this factor. And you get that the derivative of y with respect to x is, I'll leave it the same way, 4y squared minus 5x to the 4, all divided by 6y squared minus 8xy. Okay, so yep, this is a review. This is the Calc 1 way of doing it. Now, of course, let's do it the same problem, but now use Calc 3. In other words, just use this equation up here. Right? So just as a reminder, the derivative of y with respect to x is minus the x partial of capital F over the y partial of capital F. So what is the capital F here as a function of x and y? It's just x to the 5 minus 4xy squared plus 2y cubed. Now you might say, wait a minute, originally this was, f was equal to 0, not 12. So that's a fair point, but we could also just subtract 12 from both sides, and then it does equal 0. Okay, so it turns out that the constant 12 didn't matter, right? When you take the derivative of 12, you're just going to get 0, as we did right here as well. So yep, now just take both partial derivatives. Let's take the x partial. That's going to be 5x to the 4. Right, minus 4y squared, right, plus 0 minus 0, right? And then the y partial will be, let's see, negative 8xy, right, plus 6y squared, right? So now you just divide them, and then don't forget the minus sign. So having done that, the derivative of y with respect to x is just negative 5x to the 4 minus 4y squared all over 6y squared minus 8xy. right? So you can see we get the same thing here. If you distribute the negative to the numerator here, you do get 4y squared, positive 4y squared, right? Minus 5x to the 4. Right? All divided by the same denominator, 6y squared minus 8xy. Right? So, yeah, not exactly that much easier, but it's something you should get used to. Right? Because in some cases it'll be much more difficult to do it directly using the Calc 1 method than versus the Calc 3 method. Right? Right. And for another thing, we can also we can also do this for a function of 3 variables. If you have x, y, and z in your equation, right? Then try to use the Calc 1 method, and it's not gonna be quite as simple. So let's maybe do one of those. I gotta clear it. Okay, so here's the more general theorem I was just mentioning. W is a function of x, y, and z, right? And this equals 0. I forgot to mention that this is an equation here. And then z is a function of x and y, little f of x and y. And the idea is we want to find the partial of z with respect to x and the partial of z with respect to y. And, well, by the chain rule and implicit differentiation, here they are. Okay. Excuse me. So here's an example of that, right? Suppose x times e to the yz minus z times the cosine of y is equal to 0. Right? Find the two partial derivatives, partial of z with respect to x and partial of z with respect to y. So, yep, if you're trying to solve for z as a function of x and y by itself, you're not going to be able to do it. Because I can't do it either. Yeah, I mean, this is a transcendental equation, right? Trying to solve for z here is kind of hopeless. So we're not going to be able to do it that way, right? So we have to use these formulas up here. So let's just apply them. So let's start with the x partial of z. So this is minus fx over fz, and you can see it's just flipped, right? The x goes to the numerator, the z goes to the denominator. So that's a good way to remember them. But they're on your formula sheet, so you don't have to remember them. Okay, but once you get used to them, it's probably not that hard to remember. All right, so don't forget the negative sign in front here. So the partial of f with respect to x. Well, you know what? We didn't write down what f is. So maybe we should start with that. I mean, we could do it in our heads, but so f of x, y, and z is equal to x e to the yz minus z cosine y. And that does equal 0, so we don't have that issue here. And you can see we need all three partial derivatives. So before we start writing down the x and y partials of z, maybe we should just find the three partial derivatives of f, starting with partial of f with respect to x. So I think we just get e to the yz, right? And then the partial of f with respect to y, or f subscript y. So let's see, z is a constant, so we bring that in front. We get x times z times e to the yz. And then the derivative of cosine is negative sine. So we're going to get a plus z times sine of y. Right? So yeah, that's a long one. And finally, the partial of f with respect to z, or f subscript z. So now we get xy. Oh, I'm going to run out of space here. Sorry about this. So I'll do it down here. Okay. So with respect to z. Y is a constant, so you get x times y times e to the yz, and then minus cosine of y, right? Because there's your z. All right, now we can use these formulas to just write down partial of z with respect to x. It's going to be negative f sub x, so that's this, e to the yz, divided by the z partial of f. So that's this long denominator here. We get xy e to the yz minus cosine of y. Okay, that's, highlight the whole thing. That's the x partial of z, right? And then the y partial of z, yep, so that's going to be, oh, yeah, minus fy over fz. So fy is this thing up here, so we'll just copy that down here. Xe e to the yz plus z times sine of y. And then the denominator is the same as it was before. It's this thing here, so xy e to the yz minus cosine of y. And this is it. I don't see any point in trying to simplify any of this. So I think this should do it. Yep. So, right, so this would be pretty much near impossible to do directly. To try to solve this for y, try to solve it for z as a function of x and y, and then take the two partial derivatives directly. Yeah, good luck with that. That's going to be very difficult, if not impossible. But using the chain rule, using the implicit differentiation equations up here, it's really not that bad. It's just taking the three partial derivatives of f, capital F, right? And then just writing them down using these two formulas up here. So I hope that's okay. Okay. I think I got this from the book. I think it's 36 in the 11th edition. It might be 34 in the 10th edition. I don't remember exactly. But in any case, here's the problem, right? We have the equation x squared plus y squared plus z squared minus 5yw plus 10w squared equals 2. And we want to find the partial of w with respect to x, y, and z. Okay. So, yeah, this is going to be an equation in x, y, z, and w, right? And it all equals 2, but we can subtract the 2 from both sides, right? So it's going to be x squared plus y squared plus z squared minus 5yw plus 10w squared minus 2. And now it equals 0, so we can, of course, apply the same rule here, except notice that we need one more partial derivative, so we need, right, we need the partial of w with respect to x, y, and z. So w is the function of x, y, and z here, right? So, right, so the partial of w with respect to x will just be minus fx over fw. Partial of w with respect to y will be minus fy over fw, and partial of w with respect to z will just be minus fz over fw. So we need 4 partial derivatives here. First, with respect to x, you just get 2x, right? With respect to y, you get 2y minus 5w. With respect to z, it's just 2z. And then the denominator, with respect to w, the w partial of f is going to be negative 5y plus 20 times w. Right. And of course, the negative 2 is a constant for all of these, right? So I think we can just write down the answers here. So negative 2x divided by, let me squeeze this in here, negative 5y plus 20w. Of course, maybe we can write that with a plus 2x over 20w minus 5y. Oh, I got it backwards, right? 5y minus 20w. Because I'm bringing the negative downstairs here. Right. So yeah, 5y minus 20w. Okay. So now partial of w with respect to y. So that's minus y, so 2y minus 5w divided by fw, so negative 5y plus 20w. And we can simplify that a little bit by bringing the negative downstairs. There we go. Let's see, can we, yeah, I don't think we can, if we factor out the 5 here, we get y minus 4w. Nothing cancels, so why bother? And finally, the z partial of w. So minus fz, that's just minus 2 times z, divided by, same denominator, negative 5y plus 20w, and bring the negative downstairs. That might be nice. You don't have to, but in my opinion, it makes it look easier. It looks nicer, maybe. Not that it's easier, but it's that it's nicer. So these are the 3 partial derivatives that they were asking for. Right. So, yep, the point is you can extend this to a function of 4 variables, or 5, or 6, or a million. It's just more partial derivatives and more equations to worry about. But it's really not that much harder. It's just more bookkeeping, right? It's just harder to keep track of all these partial derivatives and which one is which, right? So that's the idea of implicit differentiation. Okay, so here's another one from the homework. I think it's number 50. So probably not one I asked for the homework. Then this is just the ideal gas law. We've seen it before, right? P times V equals M times RT. I think that should be an N for the number of moles, but okay, the book has an M there, I guess for mass, but right, so then R is might not be the same R that I'm thinking of, but okay, so doesn't matter. M and R are constants, right? P is the pressure, V is the volume, and T is the temperature of an ideal gas. So P, V, and T are the variables, right? So these are the variables here. Right. M and R are the constants. And what we want to find is the derivative of the temperature with respect to time. All right. So I think we can just apply the chain rule directly, right? In fact, we can solve for T here. It's just P times V divided by M times R. And remember, M and R, that looks like an N, because I think, subliminally, I think it should be an N. Doesn't matter. All right, so this is temperature in terms of pressure and volume, right? In other words, it's T as a function of both P and V. So in order to find the derivative of temperature with respect to T, well, we take the partial of temperature with respect to the pressure, and then the derivative of pressure with respect to T. Yep, I don't think that's a partial, right? Plus the partial of the temperature with respect to volume, and then the derivative of volume with respect to T. Okay, so I think we can find these partial derivatives pretty easily with respect to P, right? Then V is the constant, so you just get V over MR. And then the partial with respect to V, right? Now P is the constant, right? So this is P over MR. So plugging that in, well, we can factor out the 1 over mr. And then with respect to p, so we just get v times the derivative of p plus p times the derivative of v. And I think that's as far as they want us to go. Right, v for volume, not velocity or anything here, right? Yeah, so this is an expression for the derivative of the temperature with respect to time, right? Right. So of course we have to know how pressure is changing through time and how volume is changing over time, in order to plug in any numbers to do any calculations. But I think that's all they wanted here, right? So that's just a direct application of the chain rule. Okay, so here's a fun little problem that I adapted from the homework. So I think number 13 and 14, similar to this. You have two particles moving on a plane, on the xy plane. And the first particle, right, this is the position of the particle at any given time t. It's t squared I plus 4tj. And for the second particle, particle 2, its position is 3 times ti plus t squared j. And the question is, at what rate is the distance between the two particles changing at t is equal to 1? Okay, so we need the distance between the two particles, right? So I'll use, I guess, d for distance at any given time, right? It's essentially the distance formula between 2 points in space, right? It turns out to be the magnitude of, right, r1 minus r2, or vice versa. I'll say r2 minus r1. Right? It's just the norm of that vector. Right? In other words, it's going to be the square root of x2 of t. Well, we know they're all functions of time, right? So x2 minus x1 squared plus y2 minus y1 squared. Right? So usual distance formula. Yeah. So what that means is d here is going to be a function of x1, x2, y1, y2. Not necessarily in that order, right? And maybe we should be clear here, right? x1, of course, is just t squared. y1 is 4 times t. x2 is 3 times t. And y2 is t squared. So I just get those from the given position vectors, right? You can think of each of these as parameters here, right? So, yeah, we essentially have 4 variables with respect to t here, right? So we can apply the chain rule. In this case, actually, before we do that, of course, we could just do this directly, right? We don't need the chain rule here. So if you want to do it directly, here's what you're doing. Right? This is 3t minus t squared squared plus, and then y2 is t squared, right? Minus y1, which is 4 times t squared. So if you'd rather do it directly, this is d as a function of t now. Right? And so just take the derivative. All right, so maybe we'll do it that way. All right. Okay, so d prime of t, right? Because I hate writing dd over dt. That just looks really weird. yeah, so d prime of t, the derivative of d, the derivative of the distance with respect to time. Okay, so that's the rate of change of the distance between the two particles. So this is a square root, right? You're just going to get 1/2 times that to the negative 1/2. Of course, I could easily run out of space here. So the negative 1/2. And then we have to take the derivative of what's inside. So that's not going to be easy. We're going to get 2 times 3t minus t squared times 3 minus 2t, and then plus, again, another 2 times t squared minus 4t times 2t minus 4. Great. So look, at this point here, I don't think we really need to multiply all this out and simplify, because remember, we're looking for the rate of change of the distance between the particles at a specific time, at t is equal to 1. So now is the time to plug in t is equal to 1. It should be a 1 here. Right? So everywhere you see a t, just change it to a 1. So this is 1/2. Oh, we can easily pull out the 2 here. Anyway, okay, so I said I wasn't going to simplify. Fair enough, right? So look, 3 minus 1 is 2, so that's 2 squared, plus 1 minus 4 is negative 3, also squared. And then this is to the power negative 1/2, so 1 over the square root of that. And then we get 2 times 3 minus 1 is 2, times 3 minus 2 is 1, plus 2 times 1 minus 4 is negative 3, and then 2 minus 4 is negative 2. So let's see here. So we have 1 over 2 times the square root of 4 plus 9. I should have just said 13. And then this is going to be 4 plus 6 times 2 is 12. So I think we just get 16 over 2, which is 8 over the square root of 13. Or if you prefer, 8 square root of 13 over 13, if you prefer to rationalize the denominator. But that's the answer. And we never gave you units here, right? So we didn't say position is in meters and t is in seconds. You know, then you would have to say, you know, meters per second. But we didn't give units, so just, you know, natural units. It's just a pure number. And what is it? Approximately 2.2188. Right, again, distance over time. So meters per second, miles per hour, feet per second, doesn't matter. So that's the approximate. Right, so that's the rate of change of the distance between the two particles. So at that time, the particles are getting further apart, right? Right. This could have been a negative number, in which case the particles are getting closer together. The distance will be decreasing. Okay, even though distance is a positive quantity, the rate of change of the distance could be positive or negative, depending on whether they're moving apart, right? So if the two particles are moving apart, right, then the derivative will be positive. If the particles are coming together, the derivative will be negative. Or obviously if the distance is not changing, then the derivative could be 0. Or if the two particles are moving, let's say, right, in such a way that their velocities are equal, then the distance between them will not change. As they just move further and further along, the distance will stay the same. And so the derivative of the distance will also be 0 in that case as well. Okay, so again, we did this directly. I have a feeling they wanted us to use the chain rule. However, you know, they didn't. The book did not specify this. So for my money, I just kind of preferred to make the substitutions here into this formula, and then just directly take the derivative using Calc 1. But yeah, so the other way would have been to use the chain rule, which would have you do, and I really should have used s here for distance. Now I really regret. Let's call it s instead of d. So so we want the derivative of s with respect to t. It would be the partial of s with respect to x1 times the derivative of x1 plus partial of s with respect to x2 times the derivative of x2, and so on, right? Then the partial of s with respect to y1 times the derivative of y1, ordinary derivative, right? And finally, partial of s with respect to y2 times the derivative of y2. And I think that would have worked as well. Probably just as easy. All right, it's not going to get any harder than this. I do love the question about the Cauchy-Riemann equations. For those of you that are going to take a course in complex analysis, and that might be, a couple of years off, you got to probably take courses in differential equations, linear algebra. But a course in complex analysis or complex variables might be the easier of the two. You might want to do number 53, which has to do with the Cauchy-Riemann equations and rewriting them in terms of polar coordinates. But most of you, I don't think, are going to ever get that far. Although I don't know. Maybe you will. I mean, look, if you take a course in mathematical methods in physics or engineering, you very well may see the Cauchy-Riemann equations. Possibly. But if not, then don't worry about it. Right? So I don't think I asked number 53 in the homework. If I did, consider it kind of a challenge question. It's not an easy one. But this question here, this example we did here with the two particles, I think very reasonable. Either way, using the chain rule or just doing it directly. So I hope that helps.